Hey everybody, in this video I want to talk to you about derivatives. We're just going to do a brief introduction to the concept of derivatives, and I want to start by talking about the relationship between slope and rate of change and secant lines and tangent lines and derivatives and all that fun stuff. So let's begin with something that you should be very familiar with, the slope formula. You should remember this from algebra. The slope formula is m equals y2 minus y1 all over x2 minus x1, where the x1 and y1 and x2 and y2 are points on the line. And you might remember the instructor mentioning that slope is a rate of change. In other words, the rate at which one thing changes with respect to another. A very common example of rate of change that we are all very familiar with is like miles per hour. So in other words, the rate at which our distance is changing over time. So as we go through this tutorial, keep in your brain that slope is just a rate of change. So from here, we can talk about the slope of a secant line. A secant line is a line that passes through 2 points on a curve. In the figure that I have here, this green line represents a secant line. You can see that it passes through this curve at 2 points. The slope of the secant line represents an average rate of change. But in calculus, we're interested in instantaneous rate of change. In other words, the slope of a curve at a single point. So to talk about that, we need to talk about tangent lines. A tangent line is similar to a secant line, but a tangent line only touches the curve at 1 point. In the same figure that I had up before, this blue line represents a tangent line. Notice that it just touches the curve at this 1 point. The slope of a tangent line represents that instantaneous rate of change that we're after. In other words, the slope of the curve at that 1 point. So you might be wondering, how do we go from average rate of change to instantaneous rate of change? In other words, what's the connection between the secant line thing and the tangent line thing? Well, we start with a secant line that includes a point of tangency. And then we let the distance between those x values get closer and closer together. If we let that distance be h, then we can say it this way. We let h get closer and closer to 0. And as we do, the secant line becomes the tangent line. So I have here a visual of the situation. So we're basically progressing through these graphs, 1, 2, and 3. In the first graph, we've got the tangent line, and we have the green secant line. And notice that the distance between the x values is kind of highlighted here with these dots. And this is the distance. The distance between those x values is what we refer to as h. Also notice that the secant line and the tangent line share this point right here. So that's the point of tangency. As we let this distance of h get smaller and smaller, so we start out with this first drawing where h is this distance apart, and then in the second drawing it's getting closer together. Notice that as this distance h gets smaller, these points get closer and closer together, and from the first drawing to the second drawing, the secant line is closer to the tangent line. So do you see in the second drawing how as h gets smaller, the points get closer, and the secant line is getting closer to the tangent line? Then in the third drawing here, this distance h is almost 0. So that gap is closing even further, and it's almost completely closed. And you can see that those 2 points on the secant line are actually becoming 1 point, and the secant line is becoming the tangent line. So as we let that distance of h, as we let the distance between the x values get closer and closer and closer together, the secant line becomes the tangent line, and that average rate of change becomes the instantaneous rate of change. I've got it here typed on the screen if you do better reading. As h gets close to 0, the average rate of change, in other words, the slope of that secant line, becomes the instantaneous rate of change, which is the slope of that tangent line. So that might seem kind of boring, and it almost might seem kind of like, duh. But that's the connection between, that's how we get from slope to secant lines to tangent lines and then finally to derivative. So now that we've got that all cleared up, hopefully, let's talk about derivative. So the derivative is the slope of the tangent line to a point, to a curve at a point. In other words, the derivative represents that instantaneous rate of change. And in formula form, we denote derivative using this notation here. So it looks like function notation, but we've got a little tick mark here after the f. We read that as f prime of x, and that's what denotes the derivative of a function. In other words, that's what denotes the slope of the tangent line. And so the formula of derivative is the limit as h tends to 0 of f of x plus h minus f of x all over h. And this is just basically a version of the slope formula that we know from back in algebra. Okay, so just to recap, this is the important part right here. So the derivative is the slope of the tangent line to a curve at a point. That's the instantaneous rate of change. That's the slope of the tangent line. And then this is the important guy as you're working problems, the formula for derivative. So you might be wondering, okay, what's the connection between all this stuff? Like, let's kind of try to put this all together. So I've got a pretty crude drawing here of a function, like a upside down parabola. And I've got two tangent lines, a red tangent line and a blue tangent line. We'll call them tangent line A and tangent line B. So we know that the derivative is the slope of the tangent line. And we know that slope is a rate of change. So the derivative, the slope of a tangent line, is basically telling us the rate of change of the curve at a point. And that's what we call the instantaneous rate of change. Looking at my drawing here, notice that tangent line B, the blue tangent line, is much steeper than tangent line A. Remember, slope and steepness are the same idea. So since that tangent line B, that blue tangent line, is steeper, that means that the rate of change is higher or faster at this point than at this point on the curve. So it might be helpful to think of it this way. Think about this curve as representing the path of like a ball thrown upward. So you throw a ball up, it reaches the high point, and then it comes back down to earth. The ball slows down as it goes up and reaches its highest point, right? It slows down as it reaches that highest point because it's got to turn around and fall back to the ground. So it makes sense that the slope of the tangent line at this point, which is close to where the ball gets to its highest point and then turns back around to come to the ground. It makes sense that that tangent line is not as steep because the speed of the ball is not as fast as it is when it turns around and falls back to the ground. Because as the ball reaches at the highest point that it's going to reach and then falls back down to the earth, its speed then picks up. So it makes sense that at this point, the ball is coming back down to earth, its speed is higher, and the slope of the tangent line is steeper. So in words, the ball slows down as it reaches its highest point and makes the turn to come back down. In other words, its rate of change, or its speed, becomes slower, smaller. And so it makes sense that the slope of the tangent line is less steep. In other words, it makes sense that this red tangent line is not as steep as the blue tangent line because the ball is going slower. Its rate of change is slower. But then when the ball comes back down to earth, it gains speed. So its rate of change is faster. And the tangent line, this blue tangent line, is more steep. So hopefully that helps put it all together conceptually. Okay, let's do an example. So if you want to find the derivative of a function, we need to call upon that formula that we just talked about. So the derivative is denoted by f prime of x, and the formula for derivative is the limit as h tends to 0 of f of x plus h minus f of x all over h. We're going to apply this formula to this function. F of x equals 6x squared minus 5x minus 1. Okay, so the formula basically consists of 3 parts: f of x plus h minus f of x, and then divided by h. I recommend when you do these problems that you kind of divide and conquer here. So the first thing that we want to do is figure out what f of x plus h is equal to. And to do that, we need to remember that when you have function notation and you have something here in parentheses, that means that we need to replace x with whatever's in parentheses. So instead of 6x squared, I'm going to write 6x plus h squared. Instead of minus 5x, I'm going to write minus 5x plus h, and then minus 1. So this represents f of x plus h. Then my formula says to subtract f of x. Well, f of x is just the original function that we started with, so it's just 6x squared minus 5x minus 1. And then we're going to divide all that by h. So let's put all this together. The derivative f prime of x equals the limit as h tends to 0 of f of x plus h, which is 6x plus h squared minus 5 times x plus h minus 1. And then we subtract f of x. Now be careful here, because when we subtract a function, we need to subtract it as a family, and to keep it together, we need to put it in parentheses. So this is a critical step because it's going to remind us to distribute this negative. If you miss this part, it will mess up your derivative calculation. So remember, when you get to this point where you subtract f of x, just be sure to put parentheses around the function. Okay, so we've got f of x plus h minus f of x, and then we divide all of this by h. So for now, I'm going to ignore this part of the formula, and I'm going to work on simplifying this monster over here. The first thing that will be helpful is if we multiply out this x plus h squared. So let's, as an aside here, let's single out 6x plus h squared, so we can figure out what that equals. This is essentially 6 times x plus h, x plus h. And if we FOIL or distribute this x plus h times x plus h, we get x squared plus xh plus xh plus h squared. And if we combine these two middle terms, that gives us x squared plus 2xh plus h squared. And then of course we need to remember to bring the 6 back down to the party. So we multiply all that by 6, and that gives us 6x squared plus 12xh plus 6h squared. So after all that, we've basically just figured out this first part here. So I'm going to go back to the original formula here. So 6x plus h squared expands to be 6x squared plus 12xh plus 6h squared. So I'm going to rewrite this as 6x squared plus 12xh plus 6h squared. And then from there, we can distribute this negative 5, and that gives us negative 5x minus 5h. And then we have minus 1. And now, give myself a little bit more room here. I'm going to distribute this negative, And that's going to give me negative 6x squared plus 5x plus 1. And again, this is all over h. So I'm just going to bring the rest of this formula down here so that we don't forget it. But I'm still going to ignore it for now. Okay, once we have expanded out this whole numerator to this guy here, this is actually where the fun happens, because if you'll notice, a lot of these terms in the numerator have opposites, which means they can cancel out. So check this out. We have 6x squared and we have negative 6x squared, so those cancel each other out. We have a negative 5x and a 5x. Those cancel each other out. And we have a negative 1 and a positive 1. Those cancel each other out. We're left then with (12xh) plus 6h squared minus 5h. So that cleaned up pretty nicely. We can actually clean this up even more. Notice that in the numerator, everybody has an h. So I can factor an h out of this numerator, and it looks like this. So again, I'm ignoring some of this stuff in the formula, but I'm rewriting it because it's easy to forget. So I'm rewriting it every step of the way. At this point now I'm going to factor an h out of the numerator, which leaves me with 12x plus 6h minus 5. And what that does is it allows me to cancel that h out of the denominator. That's a key step in the process, because if we were to evaluate this limit at this point and let h tend to 0, h is in the denominator. If we allow that denominator to go to 0, then we have a problem, because we can't have a 0 in the bottom of a fraction. So eliminating that h from the denominator is a key step in this whole process. I'm going to give myself another page here so that I have more room. And so here's where we're at. We have f prime of x equals, so the derivative of f equals the limit as h tends to 0 of 12x plus 6h minus 5. And we're almost done, so hang in there. At this point, if we let h go to 0, if we let h tend to 0, then we are left with, so at the point that we're letting h go to 0, we can forget about the limit part of the formula, because we're accomplishing that right now. So we're letting h go to 0. If we let h go to 0, we essentially have 12x plus 6 times 0 minus 5. As we know, 6 times 0 just equals 0, and so this simplifies to 12x minus 5. So we would say that the derivative of f of x is (12x minus 5), the derivative being the slope of the tangent line. Okay, so you might be thinking, well, what kind of slope is this? Like, this isn't a number. Like, we're used to seeing slope as a number, right? Well, actually what we found here is a formula for the slope of the tangent line. So when you're not given a specific x value, what you're essentially finding is just a formula for the slope of the tangent line. This allows you then to find the slope of the tangent line given any x value. So let's say that you wanted to find, say, what is the slope of the tangent line to f of x at x equals 1. This derivative that we found gives us a formula with which we can find, which we can answer this question. We can find the slope of the tangent line to the curve at x equals 1 by just allowing x to be 1. So the derivative at 1, the slope of the tangent line at the point x equals 1, would be 12 times 1 minus 5, which is equal to 7. So that would be the actual numerical slope of the tangent line. So when you find the derivative, just to recap, when you find the derivative of a function and you're not given a specific point to work with, like we just did, you're basically finding a formula for the slope of the tangent line that you can then use to find the slope of a tangent line given a point. Like in this case, we were given an x value of 1, and we could then find the specific slope of the curve at that point. And just to, all right, I'm going to warn you, this is going to be pretty rough here, but our function to begin with was 6x squared minus 5x minus 1. And just as a very rough sketch of what this function looks like, it looks something like this. Okay? Actually, it's going to look something a little more like this. It's a parabola. It opens up, and put some tick marks in here. So you can graph this on your graphing calculator and verify. So a very rough drawing of this function here. I apologize, my drawing skills are not that great, but you kind of get the idea. So what we've found here is, here's x equal 1, and essentially what we have found here is if we wanted to find the slope of the tangent line at any point on this curve, so whether it was here, or whether it be here, or whether it be down here, we could plug in that given x value and find the slope of that tangent line. In this case, I told you guys that we would find the slope of the tangent line at x equals 1, which is right here. And so essentially what we have figured out is that the slope of this tangent line is 7. So it's pretty steep, and that makes sense because when we actually sketch the tangent line, it looks pretty steep. Okay, before we end this little video, another common question that you might be asked at this point is, what is the equation of the tangent line? So we found the slope of that tangent line, it's 7. To take it one step further, we can find the equation of the tangent line. Okay, so in order to find the equation of a line, going back to your algebra class, we need what? We need a slope and we need a point. Well, we already have a slope, right? We know the slope is 7. And we actually already pretty much know the point as well. We know that x equals 1. And so we can plug x equal 1 back into our function to find the corresponding y value. If we plug in 1, we get 6 times 1 squared minus 5 times 1 minus 1. So that's 6 minus 5 minus 1, giving us 0. So the point that we have to work with here is 1, 0. Graphically, that makes sense as well because it looks like the point at which the x value is 1, that the y value is 0. So we have a slope and we have a point. So we can use our algebra knowledge to find the equation of this tangent line right here. So this is nothing new. This is the new stuff is already done. The derivative stuff is the new, that's the calculus stuff. Finding the equation of a tangent line is actually, like I said, it's nothing new. It's something that you have done many times in algebra. So hopefully this will look familiar. We can start with the point slope form of an equation, which this might take some conjuring from your memory, but it is y minus y1 equals m times x minus x1. So this is what we call point slope form, and point slope form of a linear equation. Linear equation because we're trying to find the equation of this tangent line, which is just a linear equation. Point slope form is where you have x1 and y1, which represents a point that the line goes through, and then m is the slope. So we've got all the information that we need. We have our point x1, y1, and we have our m value, our slope. So we can use point slope form, plug all this information in, and get our equation of the tangent line. So y minus y1 would be y minus 0 equals the slope, which is 7, times x minus the x coordinate of our point is 1. So this simplifies to y equals 7x minus 7. And putting it all together then, we have a curve. We have found a formula that will give us the instantaneous rate of change, or the slope of the tangent line, for any point on that curve. I threw out there the point where x equals 1, so we were able to find the slope of the tangent line, or the instantaneous rate of change, right there at that single point where x equals 1. And then we even took it a step further. Since we found the slope of that tangent line, we can go one step further and find the equation of that tangent line, which we found to be y equals 7x minus 7. That's the equation of that tangent line right there.